Hello everyone, welcome to my channel, The Teaching Show. Please like, subscribe and press the bell icon for more updates. So, in this series we are looking on various problems on thermodynamics. So again we will look some problems which are based on first and second law. Let's get started. So the problem which I have selected is based on steam table. Let's see what is the problem. This is a rigid tank. Initially it contains 1.4 kg of saturated liquid water and it is present at a saturation temperature of 200 degrees centigrade. Now this saturated liquid water, it occupies only 25% of the total volume V of the container and 75% of the volume is occupied by air. Now heat is supplied till this whole saturated liquid water is converted into saturated vapor. Now it's asked to find the volume of the tank, the final temperature T2 and the final pressure P2 and the internal energy change of water. So let's get started. In order to find all these things, first of all, let's see what are the initial conditions. So we know that this is saturated liquid which is present at a temperature of 200 degrees centigrade. So what we will do is, first of all, we will go and see what are the properties of this saturated liquid water at 200 degrees centigrade. Okay. So the first thing which we see is that the specific volume is 0.001156 meter cube per kg and its internal energy, because it's liquid, so we are going to read the value UF, and the internal energy is given as 850.47 kilojoules per kg. Now let's see how much is the volume occupied by water then, because you know the specific volume is given in meter cube per kg. We know that 1.4 kg of water is present in the cylinder or whatever the container. So if I just multiply these two, we will get the volume of the water. So volume of the water comes out to be 0.001619 meter cube, but this occupies only 25% of the total container. So then the volume of the total container we can obtain by dividing this volume of water by 0.25. So the volume of the container comes out to be 0.006476 meter cube. So first part of the problem is solved. That is the volume of the tank we have calculated. Now we have to calculate what is the final temperature and pressure. Okay, so let's again see what we can find from the steam table. So what value we have? We have mass of the water which is available, that is 1.4 kg. It is going to be fixed because this is a closed system problem. So mass is fixed and the final volume, that final volume is equal to the volume of the tank, which is equal to 0.006476 meter cube. So then in the final state, if we want to calculate the specific volume, we just divide the volume of the container by the mass of water and we get the specific volume in the final state. It is 0.004626 meter cube per kg. Now we have one value. Okay, so at least we have one value, that is the specific volume at the final state. We will use this value of specific volume to find out the temperature and pressure at the final state. How will we do it? We will again go back to the steam table, since it has been given that the final state of water is saturated vapor. Okay, so we will see only saturated steam tables. So let's take saturated steam tables and locate where do we find this specific volume. So when we scan this table, what we find is that our value lies somewhere between this value of 0.0046995 and 0.0044. Okay, so our value is lying somewhere in between. That means in order to find the temperature of the steam in the final state, we have to interpolate between these two temperatures of 371 and 372. So again what we will do is we will just do the linear interpolation between these 2 points and we will find out the final temperature, which comes out to be 371.3 degrees centigrade. Similarly, pressure will be the saturation pressure at this temperature. So once we have calculated the temperature, we will again linearly interpolate between these two pressure values and we'll find out the final pressure value, which comes out to be 21.3 megapascals. Again, then, so your B part is done. The final temperature and pressure we have calculated. Now it's been asked the internal energy change of the water. Okay, we have what is the initial internal energy. We have to find the internal energy at the final state. We will again use the same values since your final state is what? Only vapor. So we will read these values of UG, okay, and interpolate between these two to find out what will be the internal energy at the final state. It comes out, if you linearly interpolate between these 2 points, what you get is 2201.5 kilojoules per kg. So internal energy U2 is calculated. So then the change in internal energy is mass into U2 minus U1. U1 is same as UF. Okay. So the change in internal energy is given by 1892 kilojoules. Simple. This problem is only based on how well you can read your steam tables. So take a look at this problem. That will clear your concepts on steam table. Okay. Now let's proceed to another problem. In this case, what we are doing, I am giving you a superheated water vapor which is at 15 megapascal and 350 degree centigrade. And I am asking you to find out the specific volume of this superheated water vapor using these 3 things. First, you have to use an ideal gas equation. Second, use the compressibility chart. And third, use the steam tables. So let's take one by one all these 3 methods. Okay. For this, I need specific gas constant for water, which is given by which is already given in the problem. It is 0.4615 kilopascals meter cube per kg per Kelvin. Critical temperature of water is 647.1 Kelvin and critical pressure of water is 22.06 megapascal. So ideal gas equation, application of ideal gas equation is straightforward. V is equal to RT by P. Okay, R is given, T is also given, P is 15 megapascal. Okay, since R value is given in kilopascal, so I am changing this value of 15 megapascal to kilopascal. Okay, so I get the value of specific volume from the ideal gas equation as 0.01917 meter cube per kg. Let's now use compressibility chart. Okay, so you know what compressibility chart gives you. It gives you compressibility factor as a function of reduced pressure for different reduced temperatures. Okay, so on x-axis I have plotted reduced pressure. How do I calculate reduced pressure? Reduced pressure is nothing but the given pressure divided by the critical pressure. So given pressure over here is 10 and the critical pressure is 22.06 megapascal. So my reduced pressure is 0.453. Similarly, I am going to find out what is my reduced temperature. The given temperature is 350 degrees centigrade or 673 Kelvin. My critical temperature is 647.1 Kelvin. So the reduced temperature is 1.04. Now I will go and locate these in this compressibility chart. So first of all, let's fix it. What reduced temperature we are seeing? This is for 1, this is for 1.05, 1.1. So these are for different reduced temperatures. So let's say 1.05 is the closest to our value. So I am going on this curve. Now I have to go to which point? I have to read the value of Z at pressure equal to, reduced pressure equal to 0.453. So this is 0.5. It will be somewhere over here. If I go on this curve, what I find is that it's approximately 0.85. Okay, so my Z value is approximately 0.85. Now in order to calculate this specific volume, I will just multiply my specific volume which I have got from the ideal gas equation and multiply it with the compressibility factor Z. So if I do this, I get my specific volume as 0.01629 meter cube per kg. Okay, now we will see the third method, that is from the steam table. So steam is at 15 megapascal. Okay, and its saturation temperature, if I go to saturated steam table and see the steam at 342.15, then its saturation pressure is hold on, let me see. Okay, so I am directly using a superheated steam table over here. So this is the values, these are the values at 15 megapascal. We see that saturation temperature at 15 megapascal is 342.15. You can also go and see this value in your saturated steam tables. Okay, if you go to 15 megapascal, you will see that the saturation temperature is 342.15 degrees centigrade. So my steam is at 350 degrees centigrade, so that means it is superheated steam. Okay, you can easily now calculate what is the degree of superheat. 350 minus 342, so approximately 8 degrees of superheat is there. Okay, so now I have located this 350. The pressure is 15 megapascal, so I have to just treat this value of specific volume, which comes out to be 0.01148 meter cube per kg. Okay, since these steam tables, they are the experimental values, so these are the most accurate ones. So I am going to do what? I have to calculate the percentage error. I will calculate based on these values, this value which I have read from steam table. So if I calculate the percentage error, that is this value minus the value which I calculated using ideal gas equation divided by this value again, that will give me the percentage error. So I have calculated these percentage error and I find that ideal gas equation gives me 67% error. If I use a compressibility factor to improve my estimate from the ideal gas equation, then the error reduces to 41.9%. Okay, so thanks for watching this video, and please leave a comment if you have anything to say, or if you have any confusion or you want something to be explained in detail, then you can leave a comment here and then I will try to answer it. Thanks a lot for watching, and please remember to subscribe to my channel. Thank you.